We're ready for the next presentation, and our next presenter is Stuart Bennion, also of WSP, who's one of our Assistant Vice President for Structural Design and is responsible for Southwest Washington and Oregon structural design of bridges for WSP. So, Stuart, thank you. I'll turn it over to you, and I'll show you how the keys here. You can just do the down button here,
okay,
and you should be good.
Perfect. I'm glad to get to be with you, and especially with Lee and Mervyn. Being aware of time, I developed my presentation so that I could make it quicker or shorter. We have a design document here that has a lot of great information that has taken a team of really experienced men and women to put together, and then we were asked to create design examples. And out of this document that's about 180 pages long, the design example is a little over 107 pages. And I have 20 minutes to go through it. So I really can't go through it in that degree. So my goal today in presenting this is to help us understand that this application just gets a little more complicated. It's not that it's really that challenging. It just takes a little bit for your mind to wrap around what we're trying to do with performance-based seismic design. We're trying to give the engineers the ability to control the design with better understanding of what they're doing, rather than what I'll say historically, when I first started as an engineer, was the black box force base. I was creating ductility and I just didn't really understand why. Lee's already pointed this out, and I would like to say we're making good steps towards getting here, but there's a lot of knowledge gaps, and there's a lot of things that we still need research out there to help develop. To simplify this design example process, I'm going to talk more about the story, because as an engineer, it's really easy to get wrapped up in the numbers. As a researcher, it's really easy to get wrapped up in the numbers. I want to be able to prove the process. When you come to practice and you sit with an owner like Elmer, and you sit across the table and you say, what do you really want to get out of this? He's got a limited budget. He's got a project goal. He's got things he wants to have done. And I can analyze it in lots of ways and come up with lots of solutions. So how do I meet the goal of the owner to get the performance that we want out of the structure? But a lot of times the owners care about a lot of things, not just the seismic performance. And some of them don't make a lot of sense to us as bridge engineers. We don't care why you care what the column looks like from a pigment or an architectural standard that's on there, but to them that can be very important. So we're going to talk about the purpose and goals of the project, the first couple of steps in the PBSD process. We sit down with the owner and we identify that this is an ordinary bridge, except that on the other side of this creek is a bunch of farmland. And if they were to lose at a lower level event this bridge and the access to it, these farmers would lose their livelihood. It could happen during a farming time period. Again, as a bridge engineer, what does that matter to me? But they want to be able to have immediate access to these farmers right after the lower level event. So we're going to take what would come in this process for determining the performance levels. An ordinary bridge, we've generally designed to PL3 and PL1 for the lower and upper level respectively. And we're going to do that, except we're going to modify PL3 to PL2. And the reason I wanted to walk through this is I want you to understand that these guidelines set up a whole bunch of parameters, and you as the engineer get to change them. You get to modify them. They become a bunch of puzzle pieces that you can put together as you need. So to do that, we're now going to work in the operational PL2 level instead of the PL3 strain limit levels for this design example. And we're still going to perform the same PL1 life safety criteria. So moving forward, we now sit down with the owner and we try to understand the goals of the project. From their perspective, they want a conventional concrete bridge, low maintenance, low cost. They want architectural columns because this happens to be a gateway to a whole pedestrian bike facility. People see this bridge all the time and they want it to look good. They've got a standard throughout the corridor of using these architectural columns, and they want to maintain that. All right, we can work with that. They want enhanced seismic performance. They want to be able to get to the farms, and they want to be able to do this at these two different design level events. Now, this is what's in the guidelines, but I know of other states that actually have other performance level events that are already codified in their state documents. And that, again, is acceptable. You can define the hazards that you want to design to. So now we develop the bridge layout. We're in New Madrid, Missouri. We're on a straight alignment without any skew. We are a two-lane state route with median barriers, no pedestrian traffic. We have a tributary stream of the Mississippi River. And we have interior piers within the ordinary high water. So we have the site access to recreational activities already talked about. We have a 2-foot design scour below the creek and a whole bunch of other design inputs that come in on the civil side. We got to take care of all of these things. They don't just disappear, and we don't just worry about the earthquake. So here's a quick picture of what this bridge looks like from an elevation view in a typical section. To define a little bit more of the bridge geometry that we used, we used 3-span pre-stressed concrete girders that are continuous for live load. We have cast-in-place decks and barriers. We have a semi-dropped 2-stage crossbeam. We have 2 column vents separated on pile-supported footings. Those footings are 22 by 16 by 6 foot deep with 4 rows by 3 rows of piles. There's no interior piles at the column. And then we have reinforced concrete filled steel piles that are 1/2-inch wall, 18-inch diameter piles. This is all important because this plays into the soil spring stiffnesses that we need to generate. Now here's the column that they asked for. It's a concentric spiral interlocking columns. As with all of the, again, Lee mentioned that this guideline supplements and complements the seismic design specifications. So with that, we start out with designing the column for surface and strength. We make sure that we have what we need to handle the normal demands on the bridge. But as in this case, we were less than 1%, so we bumped the steel up to 1% for what we need. So that's our starting point. Now note in this graphic, we don't have all of the ties and the bars that are required in the code. We just wanted to do that for simplification, but they would be there as well to meet all of the standards. Let's jump into the next steps, which is defining the hazard. As we said, that interaction is a problem. So again, we're in New Madrid, Missouri. Here we're using the USGS process for defining, again, 2014, process for designing the lower and upper events. So you can see the site factors here. And the soils, they've been evaluated for the geohazards, so there's no special design for settlement, fault rupture, liquefaction, or slope stability. We plot that map, and note there is a typo here. I realized that my D1 dropped off, so it just says D, but to the new guides, this would be a D1 site. And then we define the earthquake resisting system. We're going to define the principles that we want to design to. Again, we're controlling all of this as an engineer. Now, I'm making a decision to not use the knockoff back walls and not account for the abutment resistance in the design. That is a tool that you could use to play with this if you want to, but we're not going to. I'm also not going to use the breakaway shear keys. I'm going to pin this at the abutments and make sure that my girder stops can handle that shear force. So now let's jump into the design. Here's where you actually start to control, and we talked about using extract and sap to be able to develop our curvatures and our performance. Here is where you input those strain limits. Here is where you define this depending on which hazard you're designing to first. We're going to start with the upper level event just to see what the performance of these rectangular columns are and what they want to do. And then we're going to step back through that with the lower level event and make sure that we're still getting the performance that we want. So here we input all of these data. And here's an example, because this is a rectangular column. What I showed before was one variation of what you see on your left side of the screen. for the longitudinal direction. Similarly, we generate the curve data that we need for the transverse direction. And then we iterate in on a whole bunch of spring properties. These properties are provided based on the types of soils. We've assumed 4 sand layers, 2 that are applicable at the interior piers. We have used the larger elastic forces to develop the springs. So what we're saying there is we're assuming we're going to form a plastic hinge. We're taking the plastic capacities and we're using those to generate and iterate in on these spring stiffnesses, and then we're using that model to come back into our bridge and make sure that we're performing at that level. Later, we're going to validate that that assumption was true. I'm not going to get into that now, but all of those validations and steps are very important in your process. So we're going to ignore the passive soil participation at the abutments. We're going to incorporate the pile group effects with 4D spacing. We're going to talk about or include the pile connection to make sure that the interface of that reinforced concrete in the pile to the footing is developing the plastic capacity, the capacity protection resistance that we want, and then that the shear reinforcement in the piles and in the columns are adequate to develop the ductility. Note that these piles were designed first for surface and strength, so they were controlled in the depth based on the axial demands of the bridge, not by the lateral performance of the bridge. So that's not something we had to iterate back and forth on, but in your design you could. And be really careful there. I was talking to Professor Marsh just yesterday about this. If you're in a zone where that sensitivity is messing up your model, just lengthen them. Get out of that sensitivity zone and get that out of your analysis. So we jump into the fun stuff and it just magically happens. It's really important that you validate your models. You actually make sure all of this is performing and working right. You're in control of it, and it's easy to have a black box telling you something that you actually have no understanding that it's even doing anything that you would plan on it doing, but it gave you an answer. So if you can't go back and hand check some of this stuff, if you can't convince yourself that it's right, don't trust your model yet. You don't know that it's right. So we validate the model, we make sure it's performing the way we want, and we get the displacements out of it that we need. Ultimately, that's really all we're doing all of this analysis for, is to get an accurate displacement so we can verify that we're getting the performance that we want, and to check the limits of the strains down in the bars to make sure we're getting the ductility and the performance we want. So it's a lot of work to get to a very simple answer, but you can do a lot wrong to get to this point. So we check the ductility demand of these rectangular columns, and lo and behold, we're at 6.4, and the code requires us to be at 6. So we can play a game now. We're the engineers. We can start talking about abutment stiffnesses. We can start talking about adding more steel into the column to start getting that ductility to a level that we want. We can control this. So we now need to go and talk to the owner, because we got some choices to make now. Before I even go talk to the owner, I go, you know what? What if I just go back to more conventional reinforced concrete columns? What's the relationship of those? Let's just look and see what a circular column would do. And when I do that, I find that I'm 34% and almost 50% higher in the transverse direction with this rectangular column than what I actually need for this bridge, if I want to just design it with a rectangular column and change this architectural goal of the project. So if I don't do that, and I want to get to the performance level that I'm asking for and the ductility checks I need to make, my foundations are going to start blowing up. They're going to get really expensive really fast, because I have to start increasing what's happening in the column and chase that through the substructure. Similarly, I look at the longitudinal strength, and I note that that because I'm not at the ratio, I'm actually going to be making the circular column actually stronger. But relative to what I'm doing up above, getting that up to that 1.0 level and getting it to work, I'm only hurting the process up above again. So I sit down with the owner, and I walk through this with them. And I help them understand what's happening in the process. And I ask them, do you really want me to chase this in the design, or do you want to change the column? And they decide, let's change to the circular column. We do this in the design example. We then change the target, we redefine the properties, and we move on. Now here's where I'm out of time. I thought a lot about how much do I show of this whole design process. Here's the main steps. I'm going to toggle through them in about 5 seconds. There you go. We just designed the bridge. Not really. That takes a lot of work. But all that is, from that point on, is the same practice and principles that you do in the seismic design specifications. I don't need to teach you how to do that again here. It's really no different with this performance base. The performance base is coming back to the objectives. It's setting limits and looking at what we want to do. So let's walk through this with the owner real quick, and then I can turn over the rest of the time to Mervyn. So these are similar to the graphs that Lee pulled up before. This is a summary table of all of these limit states. And as you can see, all of the X's for my 100-year event are easily meeting all of the performance goals to be able to allow the farmers to come back into the property. It's not even a problem. I could have even gone to a higher level if I really even want to. And so that's something that we can now talk to the owner about. Do we want to define this as a bridge that can have a higher performance level? We can play with that. At the 1,000-year event, you can see that I'm well within the limits of the PO1 and PO2 processes that are there. Not a problem. We've got the bridge performance that we want. Ductility, I'm now down within the limits that I need to be in. But again, I got to reiterate, these are the additional checks. It's really about the model verification to make sure you're doing it right. It's the hand calculations to make sure that the processes that you're checking are good. It's the P delta effects, the R factors that you need to apply, and then meeting the minimum lateral strength requirements. Now, I did want to talk real quick about the documentation. I think this gets missed by engineers a lot. When it comes to performance, let me go back. When it came to the seismic design specifications, if you actually go back to chapter 1, there's a whole section in there about documenting what you actually do. And most of us don't ever go back and look at that chapter after we read it through the first time. We go to what we need in the code and we use it. Documentation of this process is very important, because how do they know later that what you are doing and what you've designed to is there? They can guess if they look at the steel in your plans, and they can guess if they make a couple of statements in there, but it's important that you document this information. It's even worthwhile to show them the limits of the performance and where you're at in the process, so that when the inspectors come in, if the inspectors had a sheet like this and you circled and said, oh, I'm at this level 1 over here, this is what you should see after this event, the inspectors can then go walk out there, take the bridge plans and go, yes, I'm at the performance level that they said I could be at, we can open this bridge and we can go. So this documentation becomes very important.